So now, in our final video for the week, we're going to talk about what it means for a function to be onto or surjective. So, definition: a function f from a to b is called onto or surjective if every element of the codomain B is the image of some element of A. Another way you can state this is that F is onto if F of A equals B. If the image of A is all of B. So let's look at an example. Again, anytime you come across a definition, you should probably look at an example. So let's say I'm looking at F1, a function from A to B, where A is the set 1, 2, 3, and B is the set X, Y, Z, W. B defined by F1 is going to be 1 relates to Y, 2 relates to W, 3 relates to Y. And so we want to talk about whether or not this function is onto or not. So we got to look at all the elements of B and ask, are they images of an element of A? So if I look here at my second coordinates, I have Y and W, but I don't have X or Z. So F1 is not onto, and that's because X nor Z is an image of an element of A. We could also look at this example visually. So here's A is 1, 2, 3, and here's B, which is X, Y, Z, and W. So 1 went to Y, 2 went to W, 2 goes to W, and 3 goes to Y. So if you're looking if a function's onto, then everything over here in B, everything in B needs to have an arrow coming into it. So the problem is X and Z don't have arrows coming into them. So that's why this function F1 is not onto. Now the problem is, I'll say with the given sets A and B, there is no surjective function A from A to B. So remember, in order for this to be a function, I have to have exactly one arrow coming out of everything in A. So because this is a function, at most you're going to have 3 arrows. Well, actually, exactly, you have 3 arrows coming out. But in order to be surjective, everything in B needs to have an arrow coming in. So I would need at least 4 arrows. But there's no way for me to have 4 arrows here because I said every function would only have 3. So in particular, I'll say if A and B are finite sets and F from A to B is surjective, then the number of elements in B is less than or equal to the number of elements in A. And again, this only works if these sets are finite sets. So in this case, I said there was no surjective function from A to B, but if I flip it and instead write a function from B to A, your codomain would have smaller size. So I could have a surjective function then. So G, if I instead look at the function from B to A, where G looks like x3, y1, z3, and w2, notice that all the elements of A appear as second coordinates. 1, 2, and 3 all appear there. So you can show that G is a surjective function. As 1 is an image of Y, 2 is an image of W, and 3 is an image of Z. So we're going to look at one final example here. And I want you to prove the function f from R to R defined by f of x equals 3x minus 5 is onto. So what do we need to do? We need to show every element of our set B, which is R, is the inverse image of some element in the domain R. So usually when we work with functions, we're much easier, I'll say it's much more common for us to think about plugging in numbers for x. So for example, f of 0 would be -5. But that's not what we're doing here. We're starting with an element we're looking at inverse image here. So for example, I need to find an x so that my function outputs 1. What would be the input to output the value 1? Well, that means we need to look at our equation, 3x minus 5 equals 1, and solve for x, right? So add 5 over 3x equals 6, and then you divide by 3 here, and you'd get x is 2. So I just did this with the element 1. This was a specific value, But here I need to do it for every real number, not just one, and not just here in the case of -5. But what's great is I can, instead of putting in 1 there, I could just replace it with y. So let's say, let's kind of mirror what we just did here. If I take an arbitrary value in R, we need to find an x such that f of x equals y. So 3x minus 5 equals y. And here you're thinking about y as being a fixed value, and so you want to solve for x, but you use the same procedure you did earlier. You're going to add 5, and then divide by 3, which again you can do here because you're talking about real numbers. And so right here, this is your element from the domain. This is your element from the domain. So now let's write up the proof formally. So I'll say proof. We're going to let y be in R. We show, what we're going to do is we're going to show that there exists an x in R such that f of x equals y. And that x, we're going to choose x to be, what did we say x should be? It should be y plus 5 over 3. Then x is a real number. And if I look at f of x, this is f of y plus 5 over 3, which is 3 times the input plus 5, minus 5, that's my function f. And then here, 3's cancel, y plus 5 minus 5, so this is y. So I found an input value x that outputs my value y, and since y was arbitrary, I can then conclude, therefore, the function f is onto, and that completes my proof there.